All right. So what we were discussing last week was, and where we ended, was this whole question of what was the input and output relationship between in a continuous time system. So just to draw a little block diagram here, that you had a system HT, we put an input XT, and we get some output YT. And we saw that for continuous linear time invariant systems, that the relationship between the output and the signal was that Y of t was equal to XT convolved with HT. And that the convolution itself, this expression, was in fact, another way of doing it was to an integral minus infinity to infinity x tau HT minus tau d tau, right? That was the way that you actually evaluated it. So in fact, that the input-output relationship it's a constant sort of summing process. And we went through how the derivation worked. We started with a discrete time case, and we landed up with and eventually we were able to see what the continuous time version was. Okay, so now today what we're going to do is to spend some time and do some a couple of in-class examples here, just to make sure that you have the mechanism right, how to approach it, and then there will be some other problems that we'll meet in the problem sets going forward. All right, I put a handout that has the sort of, for want of a better word, the English description of what we are about to do here with class problem 1. And we will follow that. That process is exactly the same that you would follow for any of the convolution examples that you will be meeting. All right. If at any point in time, of course, remember, try to catch my attention, say something, because I'm not always able to see the chat while I am watching while I'm watching my screen here and writing on it. So that if you need to attract my attention, just say something. All right. Okay, so let's follow it through and tackle the problem that we have here this morning. So we're given a system, and here right now, so today is more about doing the actual algebra or the calculus rather than figuring out how we came up with HT and XT. However it is, we have a situation. So XT, so this is some system and some input. XT looks like this, and HT, somehow the system response is this. And we know that in the Laplace domain, this sort of meant that the transfer function was HS, the transfer function of the Laplace transform of whatever this is. So the first step in evaluating this, remember what we're trying to do, and I'll put a blank slide here. We are trying to find out XT convolved with HT, right? So YT is equal to that, which is also equal, and the actual integral is this, X tau HT minus tau d tau, right? So from last week, we saw that to get to this integral form here, there are a couple of things that we have to do, a couple of steps. And let me just, we have the signals here on the previous slide. We have HT, which is the one in red, and we have XT, which is the one in blue. What we need to do is, of course, the first step is to define the equations that represent both of them. So what is HT and what is XT? If you watch HT from here, you notice that HT is equal to 1 once t is less than 2 or greater than or equal to 0, right? It changes at 0. So we are assuming that the change occurs at 0. So once t is greater than or equal to 0, h becomes 1. And it changes again at t equal to 2. So just before t is equal to 2, which is t less than 2, it is still 1. And then right at t equal to 2, it will now become 0. And it's equal to 0 elsewhere. Everybody following with that? You okay with that? Yeah? All right. So we do a similar thing for x now. If you look at x, xt is equal to 1 for t less than 2, less than or equal to 0. And it's equal to 0 elsewhere. Right? So we have the two equations here. So step one is always step one, if you like, on this slide here. Step one, get all right. First step is to get the equations for xt, ht. The next thing you know is that the equation is expressed in terms of a dummy variable for integration. We express it in terms of tau instead of t. Could have been anything, but in engineering, we tend to use the word tau, the symbol tau. And as we saw yesterday, or sorry, last week, h tau and x tau are the same thing. So if I were to change the variable here to tau and change this variable, it does not change the expressions, right? So step two, change variables of integration from t to tau, right? Why? Because I can't, it is, as I told you before last week, that if I'm integrating x, I can't be integrating x with respect, although we do it in AdMaths, but really and truly it is wrong to do something like this, to integrate some function of x with respect to x and have the variables as the same function, the same variable being used also for the limits of integration, right? What is really supposed to happen is that you're supposed to integrate f of something, some other variable, and the actual variable of integration, what you're using to set the limits, is what you will is what you put on the integral sign, but you do not integrate with respect to that. You have to change it, right? But we so accustomed doing this in high school that we actually forget that the reason that mathematically you can't do that. Okay, so that's why we changed the variables there. All right. And you're going to see that come up. There's a lot of maths that you will encounter that you have to do that. Okay, the next thing now is that if I change, so we go back here to the thing. So look at it. We now have, so we have x tau and we have h tau. H minus tau, we said if h of tau is looking like this, so it's going 0 to 2, amplitude is 1, right? So this is h tau. Then h minus tau is you flip this around the t equal to 0 axis. So h minus tau is this bit here. All right? And t minus tau moves to the point tau equal to t. T could be any value. So look at this carefully. If I arbitrarily pick a value of t, t could be anything. t minus tau could be something like this. And how we know is that where it is located is where the h0 point is. So for something like this, the h0 point will be h0 is at t equal to tau. So that they put it, sorry, let me put it, tau is a variable at tau equal to t, right? Which means that this is the h0 point. So this is now the point t. And if this is t, what is the size of this pulse? How long is this pulse? Anybody? How long is the pulse? One, two, three, 4 units, t units. How long is it?
2 units.
2 units, right? So if the unit, this is 2 units. If this point is t, then this point here is 2 units behind t. Fair enough? Yes?
Yes, sir.
Right? So the next step, therefore, in our here was you change the variable from t to tau and then find, right? This is sketching, some ht minus tau and put that down, right? So you now locate ht minus tau. So what we have now is that our integration is now this. We have x tau here, which is running from 0 to 2. And we have ht minus tau, which is running from t to t minus 2. Right? So step 4 now. Step 4 here is to evaluate. I'm calling this equation 1 here. Evaluate equation 1 as t goes from minus infinity to infinity, right? In other words, t here, t is going to go from minus infinity to infinity. So in other words, this bit here now, we are keeping this fixed, but as t goes from minus infinity to infinity, ht minus tau is going to start all the way back here. As t goes to minus infinity, it is going all the way back here. And then this is going to go all the way to plus infinity on that side. So x tau remains fixed. ht minus tau, as we evaluate this integral here, equation 1, t is going to be, ht minus tau is going to be moving all the way across. And as you could see, what we have to do is to evaluate, find out where the product of the two of them is and evaluate the integral at that point in time. Okay? So graphically, this is what we're trying to evaluate. Everybody following that? Again, give me a hint here. It's written in the description, but I want to make sure conceptually you understand what to do.
Yes, sir.
Right? Okay, so 1 out of how many people in class so far? 53. Oh, good. Okay, we batting good. Okay, so let's start moving T around and see. Huh?
Yes. So I just wanted to know, like when you're graphing, and you put T, does it always have to be conceptually on the left of the axis?
No,
As
no,
in,
no.
you have to
T,
consider
T.
T as anything?
You remember T is going anywhere from minus infinity to infinity. So I could have drawn it anywhere. I could have drawn it here. So T, and this will still be T minus 2. So T could be anywhere because T is running from minus infinity to infinity. Right?
Okay. Thank
I'm
you.
seeing some Adrian asking me to go over. Which part specifically, Adrian, that you want me to explain? Let me make sure.
You can go over from where is 2 units, come down.
This bit here?
And not, yeah, right there, yeah.
Okay, good. Okay, you understand, well, okay, so when we flip it around, you understand that H minus tau is this red bit here, right? That part is clear, right?
Yes, sir.
Right, and H has a width of 2 units. So H minus tau will run from here to minus here when you flip it on, 0 to minus 2. Ht minus tau means that I've taken this entire thing and shifted it somewhere along the place to the point, if I'm talking Ht minus tau, I'm shifting this right or left depending on the value of t, right? This is the t0 point here. So when I shift this up and down the t-axis to some arbitrary point t, wherever t is, like in this one, we'll use this one, somebody asked this a second ago. If I were to move it to some arbitrary point tau equal to t, this is where the front of the pulse is, because this is the front of the pulse. So I've moved it here. And since the pulse is 2 units wide, if the front is at t, the back is going to be 2 units less than that, which is t minus 2. Make sense?
Yes, I understand that.
Right. And now what we're trying to find out is the integral equation 1 asks us to evaluate this expression here as the variable t moves all the way from minus infinity all the way up to positive infinity. All right. So this is what we have to do now. So let's see how that works. Let me just clear some space here a little bit. Right. So if I go back to the diagram below here, notice that, and I'll call these zones now. Let's call this zone 1. Notice that once t is less than 0, right? Remember this bit here, this pulse is sliding along the axis. We've started it way back in minus infinity. So this was all the way back here. We're moving t from minus infinity to infinity. So this entire pulse is sliding along the time axis. Notice that once t is less than 0, there's no overlap between x tau and ht minus tau. Right? Therefore, the convolution x tau ht minus, or x tau and xt and ht, which is this bit here, right, is 0, or the integral of x tau ht minus tau, if you like, is 0 for t less than 0. Fair enough? Right? So we keep sliding t. Let's move some space here.
Excuse me.
Yeah.
So, just double checking for the overlap for when t is less than 0, because x of tau and ht minus tau doesn't overlap, it's equal to 0.
Correct, because you could only have, remember, you're trying to find the integral of this multiplied by this. So if there is no common point, like at this point in time, right? This multiplied by this, they don't exist in the same time zone. So therefore you can't find the product of the two of them. So therefore, this bit here cannot be evaluated so that the convolution is 0. There's no answer.
Understood. Thank you.
Right. Zone 2 now. Remember, we're sliding, right? And you draw it out, when you're working it out. So we have x tau here from naught to tau. Sorry, not to 2, my mistake. So this is x tau. As h, get another color here. Right. So we know into this one, I'll just draw it a little bit bigger because both of them are the same height. So we have t and we have t minus 2 coming here. This is ht minus tau. Right? So zone 2 now, look at what happens here. As t greater than or equal to 0, right? So as soon as t is greater than or equal to 0, right? This is sliding. Remember, this bit is sliding continuously, right? So imagine that in your mind. This is a continuous movement. It's not a stop, start, stop, start. We are continuously moving ht minus tau along the time axis. So once t was less than 0, nothing. As soon as t becomes greater than or equal to 0, we start to get an overlap zone, right? And as this goes, as ht minus tau goes, remember this is going to do like this. The overlap zone gets bigger as t goes this way, right? And the back, remember the back is following, right? Up until the point, we're going to have a point now where as t is sliding, so we have an overlap zone. Once t is greater than 0, we start to get an overlap. And this is going, the overlap is going to continue here until the back end of the pulse, which is t minus 2, hits this point here. Right? So once t greater than or equal to 0 and t minus 2 less than 0, which is the back of the pulse. Remember, the pulse has a front and a back, right? We have overlap. This is the same as seeing t less than 2 or greater than or equal to 0. So once t is greater than 0, we start to get overlap, and the overlap is going to continue until the back of the pulse hits this point here. In other words, the two pulses are totally one on top of the other. Yeah? And at that point, the convolution integral, the overlap zone now, right, is between, this is the point here. Remember, let me just clear this up. Just make sure that I don't have too much mess, so I'll just go over some of it a little bit. And give me the blue. So we have the blue. This is x. This is x tau here. And we have h No, excuse me a second. Yeah, sorry about that. Dr. Rock wanted to find out something. Right, and let me just draw H here. Oh, where am I? Oops. Give me my pointer. Oh. Right, so this is the overlap zone here, right? So if you look at it, the actual zone of overlap is from the lower limit of integration here is 0, which is here. The upper limit is t, and I'm integrating x. Oops. I'm integrating x tau h t minus tau d tau, right? And what is x tau? You went back to the equations. You had an equation for x tau, which is 1, right? So this is integral between 0 and t of 1. ht minus tau is also 1 d tau, right? So if you integrate that, you're going to get t, right? So that the convolution between these 2 points is t. Everybody following? Ask your questions. Yes, no, maybe. Let me hear.
So how did you resolve x tau and ht minus tau to 1 again?
Right. You go back here. You remember the first thing that you had to do, the first step, step 1, get equations for ht and xt. All right. ht is 1, right, between t equal to 0 and 2. xt is 1 between t equal to 0 and 2. And as we said, if I change the variable, if ht is this, h or tau is the same thing, didn't do anything. Xt and x tau will be the same thing. So x of tau is 1 between t equal to 0 and 2, and ht is 1 between x equals 0 and 2. Right? So when I come back here now, x tau is 1, ht minus tau, which is this bit here, right, is 1. The zone of overlap as t is moving, and what t is moving, so this is a zone of overlap. It is a function of t, so as t moves, this zone of overlap gets bigger and bigger. And at the limit of the overlap is between 0 and 2. So you integrate, so you have 0, the front is the overlap. Oops, the overlap is starting here and it's finishing wherever t happens to be. That's the zone of overlap. So I'm integrating between 0 and t, 1, which is x tau, 1, which is ht minus tau d tau. Integrate 1 with respect to tau, so you get tau, and the limits will be 0 and t. So if you work out that, the actual value of the convolution is t. Yeah? Come on, talk to me, let me hear.
Okay, one more time, sir, please.
Okay, not a problem. Right. We are moving, I mean, okay, so I'll clear it. Let's erase this a little bit. So draw back. So we have, this is x, 0 to 2. This is x, tau here. H, we are sliding h continuously on the time axis. So this is h here. This is the point t. This is the point t minus 2. right? So this is ht minus tau coming up the road here, right? So once t, the limits now, so first we have to see how long this is going to last. This is the second zone, right, that we're trying to evaluate here. Already you could see that the area of overlap is this. That's fine, right? Everybody see that? That's clear enough, yeah?
Yes.
Yes, sir.
Right. So that the limit of the integration, equation 1, which is what I'm trying to evaluate, the limit of the integration, which is where the overlap will be, where the two of them couldn't be multiplied, in other words, the lower limit is 0, the upper limit is t, and x tau and h tau are 1 each. So I could evaluate the integral, and the answer for the convolution is t. But what is it? We have to define the time zone for which this is applicable. And this is only applicable once t, if you go back to the diagram that we have here, t starts, remember the whole pulse is moving. So this is moving and t going. So the front of the pulse slowly moving here, and the back of the pulse right? Each one of these is the same pulse, right? I'm just drawing it different heights just to show. Eventually, at some point in time, t is going to be here, right? And t minus 2, the back of the pulse, is going to be right here. In other words, you will have, at that point in time, the entire ht minus tau is going to be over x or tau. Right? One pulse is going to be totally over the other one. Right? So that range, therefore, that whole overlap range covers t greater than or equal to 0 up until the point where the back of the pulse, which is t minus 2, hits 0 now. So it starts at t greater than or equal to 0 and ends when the back of the pulse reaches this point, which is this. So in other words, the total zone of overlap is now between t less than 2 and t greater than or equal to 0. And the answer is that integral. Right? They overlap the actual point where you can multiply them, and find the answer is between 0 and t. That's the overlap point. Any clearer?
Yes, sir.
Right? Anybody else? If it's there, if there's something still not clear, let me know. Okay, so that's zone 2. Let's go to zone 3 now and see. Let me get back a blue or a black pen or something. So right, good. So we have back to our x tau. Yeah.
Rashad just has a question.
Yeah. Rashad. Right. How is both of them 1 in the integral? You go back to step 1. Get equations for ht and xt, or h tau and x tau, which is from here. Notice we define them. ht is 1 between t equal to 0 and 2. xt is 1 between 0 and 2. Once we change the variables from t to tau, we're not changing that. So h of tau is 1 between 0 and 2, and also 1 between 0 and x tau is also 1 between 0 and 2. So that was the first thing we do. Remember, I told you that the first thing you have to do is to get these equations. And I could put it h tau and x tau, right? Right, so both of these kind of done together. But you need to define the equation. Once you change from t to tau, the value is the same. I've just changed the variable from t to tau. Right? Clear enough, Rashad? That is the first step. Remember, you must do that. So next zone, we're looking at another zone now. This is zone 3. So we now have this. We run this, the point where H was totally over X. This is 1 into 0.2. And we know here now, we're sliding continuously. This is tau, this is, sorry, t minus 2. This is H t minus tau, sliding continuously. So he's sliding all the way up, came from here, and this entire thing moving. So already we're seeing now, so this is the zone of overlap here. Right? So for this particular one, the convolution answer, we'll answer the range in a second. The convolution here, the zone of overlap, the lower limit is t minus 2. The upper limit is 2 x tau h t minus tau d tau. Each of these is 1 again. So you're integrating between t minus 2 and 2, which is this zone of overlap here, right? 1 d tau, right? That is the convolution, whatever that is. So there's a little bit of add maths here to do. Y t is equal to that. So y t equal to that, right? Good, to whatever that is. So you could do the add maths and the solution there. So that is tau, and the limit is 2 and t minus 2 equal to whatever. The zone now is this. Notice that this particular zone, as t moves on, this will get smaller and smaller and smaller until at some point in time, h is now like that. Yeah? So at that point in time, that is the point t greater than or equal to 2, and the back of the pulse coming as t goes forward, the back of the pulse coming. So that zone of overlap, which will now get smaller and smaller and smaller until the back of the pulse hits here, t minus 2 equal to 2. Or if you put it in one equation, t less than 4 or t greater than or equal to 2. Right? So zone 3, t less than 4, greater than or equal to 2, the answer is whatever that turned out to be. Right? You all could work out that. That's simple. That's 2 minus t minus 2, so that will be 2 minus t. So you get that. And then the final zone, zone 4, we have x tau here, 0 to 2. And then we have t minus 2. This is h t minus tau. This is the final zone here. No overlap once t minus 2 is greater than or equal to 2, or in other words, t greater than or equal to 4. All right, and that one, the convolution is 0 because there's no overlap. So that the answer, therefore, the answer has 4 parts. There's a part, zone 1, when t is less than 0, then there's no overlap. Zone 2, when t is between 0 and 2, when there's overlap and the overlap increases. Then zone 3, when t is between 2 and 4, when they overlap, decreases, and then zone 4, which is when there's nothing. So in other words, if I was to just draw that, do I have another blank slide? Just hold on. So if you look at it here, and let me see if I could use some colors here. So this is X, tau, 2, and 0. Zone 1 is this, T minus 2. That is zone 1. No overlap, right? So zone 1, T less than 0, the convolution is 0 because we have no overlap. Zone 2, as we start moving this along, we have this bit here, T and T minus 2. This is the overlap here. So zone 2, which is T less than 2, greater than or equal to 0. And we have the answer, I think, is T. And notice that this now, this increases because once T is naught, it's a function of T. So when T is naught, this is naught. When T is 2, this is 2, right? So the value increases up until the point T equal to 2. So it increases. So the convolution is increasing. And as you could see, because as this moves, this green zone gets bigger and bigger until at some point in time, we have the maximum, which is when X tau and H tau are totally overlapping each other. Yeah. Then, as you keep moving the pulse down the road, what you have now, you have X. You still have the X tau. And then you have HT minus tau. You have this. Remember, this is moving this way. So this zone of overlap now, which is zone 3, which is between T and 2, this now it reached a maximum here, and then now this is starting to get smaller and smaller. Right? So this now is equal to whatever that thing is when you evaluate this. All right? And it's going to get smaller and smaller and then eventually in zone 4, when T is greater than or equal to 4, there's no overlap again. So that the convolution is 0. Yeah? So if I'll imagine it as two the functions like two rectangles sliding over each other. One is fixed and the other one is moving. So as you move the other one, if there's no point at which they contact, and then once they start to share an area in time, there's an overlap. And that overlap, as you keep moving the pulse, the overlap area increases and increases. So the convolution increases up to some maximum value when the two pulses are one on top of the other. And then as you keep moving the other pulse, now the overlap zone area starts to decrease. And then eventually you're back to the case where there's no overlap. So the convolution goes down to nothing. So in other words, the convolution starts at nothing, it increases up to a value, and then decreases back down to 0. And a useful test to see if you have all of the zones accounted for, if you look at this thing, you notice that the convolution ran from 0 to 4, which is 4 time units. what is the total length of what is the sum of the duration of the pulses? X tau is 2 units, H tau is 2 units. 2 and 2 is 4, so that the convolution must cover 4 time units. All right? The convolution must be equal to, must have the same duration as the sum of the two functions that you're trying to find the convolution of. Make sense? Some sense?
Yes, sir. So for when you're doing a question like this, is the procedure to find for all, well, in this case, it's 4 zones. Will it be this procedure for working out a question like this, finding it for when it's before 0, when it's overlapping, and when it's completely gone past the
Correct.
XT signal?
Correct. Always. So for all the convolution questions that you're going to do, you have to identify all of the zones. So the zones before, when the convolution is 0, when it is some sort of value, and then when it goes back to 0 again. That's absolutely correct. All right.
Okay, thank you, sir.
Right. So that was the first, and this one is written up. I actually wrote the description for this, so you have that handout. What we're going to do tomorrow in class, I want you to read this, listen to this again, or watch the notes, whatever you do. Make sure you have that in place, because the next one that we're going to look at are the same 2 pulses, but notice a little difference. That X tau is the same, XT is the same that we had before, but H is now running from -1 to 1. All right. So we're going to do these things, and in fact, the ones between class and problem sets, we're going to look at the ones the ones where the 2 pulses where X and H are same time length, time duration, right? Where X and H is under are not the same time duration. In other words, where one of the pulses is bigger than the other one, right? So that's one. So we're going to look at, we started to look at this today. We're going to see a variation of that, which is the next example. Then we're going to look at the example where they're not the same, and we'll do one of that, right? At least in class, so you'll have it. And then you're going to meet now changes where X and H are not rectangular pulses. One is rectangular, one might be a ramp. And then one is rectangular and one might be a triangle, those kind of things, right? So we're going to meet all of those, and all of them for this situation where they have the same duration or they're not the same. One is bigger than the other one. Okay? So tomorrow we're going to do example 2. We will run through example 2 in class, and then we will use that to try another variation of it and see. And once you're comfortable with that, then you have the problem set questions that we will look at as well. Okay? I want to make sure you all have this down comfortable in your mind. So your sort of homework, go over what we did today, whatever notes you made in class, or and listen to the video again. Look at the scenarios that we spoke about. All right, all of the zones that we spoke about. Make sure you have it correct. Read the handout, because I put a description for it there. And once you're comfortable with that, then we'll move forward. Once you do the first two sorts of things here, the rest is very easy. There's no big set of fancy calculus inside of here. The difficulty, for want of a better word, is not difficulty, but the thing that you have to be aware of is how to identify the sort of zones of overlap, right? You see one of the functions is fixed, the other one is moving, right? So as this moves over that, right, if you sort of just imagine it moving, you will see that as one pulse moves over the other, or one function moves over the other, like what we had here in this, right. So as one function moves over the other, regardless of whatever the function is, there's a zone where there's nothing, where they don't interact. And then at some point, you're going to get a zone where they start to share the same time. That point, you need to figure out how big that zone is, and then multiply x tau and ht minus tau and find the integral over that zone. Okay? And then you have the answer. This is simple calculus. It's not no big. The problems are not to figure out if you know how to do integration, but rather to figure out if you understand the process involved. Yeah. Okay. So you probably have questions. You will have questions as you go through what we did today again. But run it through. Write down very carefully what you need clarification on. And tomorrow when we meet, we will run it through again and go on to do the other example. Okay? This one on the board down there in Ubit. Okay, so everybody all right? Relatively speaking? Yeah. Okay, so let me stop the recording here.